what's Clementine? Clementine is our bridge from Bitcoin to Citrea. It's using BitVM as a verification method on Bitcoin. It's a trust minimized bridge, meaning that as long as one of the signers, or we call it verifiers inside the code base, are honest, the bridge funds are safe. And as long as one operator is live and paying withdrawals, the bridge is live. Okay, we have a white paper. I encourage you to check it out as well. So yeah, let me dive in. So we use gRPC extensively, and this is the proto file of that. We have first verifier. A verifier's job is, so let me start with the transaction graph maybe before this. So bridge funds stay in an N of N multisig, meaning that to sign anything, to just spend that, every signer needs to sign. So these N of N, these verifiers are the members of the N of N multisig, basically. So whenever someone is doing a deposit, they first send their deposit transaction. Alice is doing a deposit, and it's locked in a taproot contract where it has two spanning paths. One is Alice taking it back after 200 blocks. The other path is only signed by N of N, and it also has an inscription of Alice's Citrea's address. And we have the verifiers do some pre-signing here. They pre-sign a lot of transactions that will be used during withdrawal time. And after doing all these pre-signings, the verifier signs this move-to-vault transaction. So this move-to-vault transaction is basically where the bridge funds staying. So the bridge funds are the bridge. Okay, this is shaking a lot. The bridge denominator is constant. It's 10 BTC, and it stays in an N of N or security council. So I will get back to security council shortly, but you can assume the money is staying in an N of N for now. So yeah, verifiers are the members of this N of N, and we sign this transaction graph for every operator and every round transaction, basically. As you can see here, the only way to spend this 10 BTC is this blue arrow, which goes to the reimbursed transaction. So we sign this reimbursed transaction for every operator, meaning that operators will be paying withdrawals, and then they will get reimbursement after doing all these transactions. Not all of it, but some of them are challenge restricted, so most of them won't be executed. We also have optimistic payout, where if all the verifiers are online during a withdrawal, they just sign this dotted blue arrow, meaning that we won't need to go through this whole BitVM process. Yeah, so we have this profile that defines what verifiers are doing, what operators are doing, and what the aggregator is doing. So these get params, set operator keys, set operator, these two are done at the time of bridge setup. Like we call a setup first, and then the aggregator orchestrates, gets all the details from every verifiers, every operators, and distributes the details. So set operator keys, this is used during deposit to set the keys for BitVM setups, and then these pre-images, the hash of these pre-images here. So nonce generation, let me also open the diagram of this one. Okay, so this is a flow of signing those transactions, and the first step is the nonce generation. So this diagram, we have three verifiers. Whenever a new deposit happens, the aggregator sends the deposit parameters. The aggregator calls the nonce generation for every verifier. So this will state how many nonces we need, and then basically verifiers return their public nonces in a stream. So there are like thousands of public nonces going through this stream, and they also have secret nonces that they need to keep secret, and they must ensure that not anything, we don't double sign anything with the same secret nonce. If we ever do that, the private key is leaked. So that's one of the things that we need to be careful as well. Okay, public nonces received. Aggregator aggregates those public nonces and then sends the aggregated nonces back to the verifiers. So using those aggregated nonces, verifiers sign the required signatures and returns the partial signatures in a stream as well. And these partial signatures gets aggregated into a final signature. This looks like a single Schnorr signature, but it's actually NFN signature. So this is what we use Music2 for. And these signatures at the deposit finalized endpoint, verified by the verifiers, saved to their databases. And after verifying and saving all the signatures, they finally sign the multiple transaction. And then the aggregator sends it basically. So yeah, we have this deposit nonce generation endpoint, deposit sign, and this is for optimistic payout signing. This is a deposit finalize. This is this step where they verify. As you can see, it has a stream of input, and it has one single output, verify, deposit, finalize, response. If you look at this, for example, it has multiple partial signature, and it also has emergency stop partial signature. So this is another transaction that needs to be signed at the end. It's basically emergency stop, sends the 10 BTC to the Security Council. There's a typo here. Just to have a emergencies transaction. So Clementine operator, they don't do pre-signing, but there's one important thing is like every operator also runs a verifier, and these operator binaries and verifier binaries shares the same database. So meaning that operators will have access to all the signatures, finalized signatures. But also, in addition to that, operators need to sign additional signatures as well. So there's also this deposit sign. But we don't need to do Music2 here. We don't need to do nonce generation here. Operators' signatures are single signatures. So let me show you, for example, an example signature. For example, this red arrow. Every red arrow is signed by the operator at the time of deposit. So this red arrow basically makes operator's collateral burned if a disapproval happens inside BitVM. So if a operator's proof is incorrect, we want to make sure that we can spend the operator's collateral, and operators gives away its signatures at the time of deposit. So this is the operator part. The operator also has withdraw and internal withdraw endpoint, which are basically whenever a withdrawal happens, users send their withdrawal details to the operators, and operators pays it, and after that gets the reimbursement. This endpoint is to get the transactions that needs to be sent to get a reimbursement of a deposit, basically. These are internal endpoints that will be useful in case of anything. It just creates all the signed transactions and returns the transactions. Yeah. Lastly, we have the aggregator. We call it setup once after we got all the verifiers connected. New deposit is basically doing this flow. Withdraw is basically distributing the withdrawal request to every operator. Optimistic payout is doing this transaction, this dotted blue arrow. It needs to get the signature of this optimistic payout. And it has some internal endpoints as well, and emergency stop transaction as well. Okay. So This is the server RS where we create a gRPC server. We give the address, and it has a config. We have a single bridge config. It has the secret key, host part, and all the DB details about Citrea's RPC, and also some certificates for MTLS. So we also do MTLS. We also do communication with MTLS to make sure that only aggregator can call an endpoint of these verifiers and operators. This is an additional security measure that we wanted to do, is like all the verifiers and operators are closed to the outside world initially, and only the aggregator can call them. An aggregator can call them only in specific endpoints. That doesn't start with internal. Yeah, this is that part. And yeah, it basically creates the server. And every server has its corresponding struct. So this is a verifier. Let me scroll down. So a verifier server has a verifier inside it, and then it has some background tasks as well. We have an automation flag, which means if the automation is disabled, the only thing the verifier is doing is basically signing transactions, but it's not sending any transactions automatically. For some verifiers, we will run with automation enabled, meaning it will send any transactions automatically. If it's disabled, then the verifier needs to send those transactions manually by calling internal generate transactions and then sending them manually. So every verifier has this struct. It has config, database, and an actor. This is the signer. It's basically a struct that's been used by operators and verifiers. It has a private key inside it. It can sign taproot transactions. And it can sign Winternet's Winternet signatures as well. That are needed for BitVM. And we also store this nonces, secret nonces, inside mutex. So, which means secret keys are stored in memory, and if something happens, we can call the nonce generation one more time as well. So let me go to BitVM as well. I need to a little bit talk about BitVM as well. So BitVM is basically a way to verify a ZK proof on Bitcoin. And whenever operator is trying to get a reimbursement, the operator sends this kickoff transaction. And this kickoff transaction is getting either challenged or it remains unchallenged. And then the operator basically sends this challenge timeout transaction. And the operator can get the reimbursement 1.5 days after that. It needs to basically send the ready to reimburse transaction, and it can get the reimbursement after sending the next transaction, because the reimbursements input includes this next round reimburse connector, which also means that if we can burn one of the collaterals here at some point, we can stop the operator. Also, if operator willingly spends their collateral to their pocket, then the operator is disqualified as well. They're gone. They cannot steal any money because they cannot send the next round transaction, and they just basically stop being an operator. So if there's a challenge, we also need to get watchtower challenges. So these watchtower challenges, when I say watchtower, every verifier in Clementine is also watchtower, and they send this watchtower challenge transaction. So this watchtower challenge transaction is basically the longest chain proof of Bitcoin compressed to a gross 16 proof. And what we're trying to achieve here is like operator needs to convince everybody that it made a payout transaction, but it can talk about a Bitcoin chain that's not that doesn't have any total work, or that doesn't have any. It's not the longest chain basically. So we want to ensure that the operator is talking about the correct Bitcoin chain. So watchtowers generate these longest chain proofs, and then the operator has to generate a proof that has a longer chain than all these watchtower challenges. So let me also show you those circuits part. So all these circuits are coming from circuits lib, and basically we have bridge circuit and work only circuit, and also header chain. I will get into that. But basically, header chain, if you look at the guest part here, it's just calling the header chain function of the circuit lib. So this is just a wrapper for RISC-0. So header chain is just, it has some network constants. We write it so that we can use it for mainnet, testnet, signet. But what it does is it has a chain state. It has like latest block, total work, and then last 11 blocks timestamps. And it also stores every block hash inside a Merkle tree, a mountain Merkle range Merkle tree. So yeah, apply block headers basically applies block headers, checks that the difficulty work matches with the target. So it checks it has enough work, and basically change the chain state. The work only circuit, it's basically verifying the header chain circuit and then just outputting the total work. So we have this circuit so that the watchtowers can send this really compressed challenge transaction. So work only proof is basically outputting the total work of a chain. And we have this bridge circuit, which is the main circuit that an operator has to prove, and then generate a gross 16 proof, and then send the BitVM transactions. So it has the input, it gets the input, it verifies the header chain proof. So it's recursively. Also, header chain proof is doing recursively. It verifies the previous header chain proof and then adds some headers and then generates a proof. This verifies the header chain proof, and it also verifies every watchtower's proof. So, and gets the maximum total work. And we want to ensure that the total work that's coming from the header chain proof is larger than the maximum of total works of watchtowers. So this means after doing this check, we are sure that the operator is talking about a correct Bitcoin chain. And we verify the payout transactions inside the proof. We verify a light client proof of Citrea. So we also want to make sure that a withdrawal happened on Citrea, and we do it with light client proofs of Citrea. We verify the light client proof of Citrea, and we do storage proofs. This is like an SP Merkle tree proof of the Citrea state, where we get the user's withdrawal out point. So this user's withdrawal out point is basically this zero value UTXO that's created by the user. And if that UTXO is spent, we say that this payout was correct. And if an operator is paying that, operator puts an op return here, puts their key there. So we do this check here. We get the user's withdrawal endpoint, and we make sure that the payout transaction's first input is that. And then we get the op return of the payout transaction, and then we get the operator's eggs only PK. This is the public key of the operator. So these, and along with these details, are hard-coded in a deposit constant. So this deposit constant is like constant during deposit. There are some parts that are not constant during deposit. It's the latest block hash, payout transaction block hash, and challenge sending watchtowers. These three values are determined during withdrawal. So challenge sending watchtowers means which watchtowers sent a challenge. If a watchtower sent a challenge transaction, then the operator has to acknowledge using this this arrow. If operator doesn't acknowledge it, then anybody can send the not acknowledged transaction after 3 weeks, burning the operator's collateral. So if an operator acknowledges it, we put 1 in that challenge sending watchtowers. This is basically a bit encoded which watchtower sent the challenge. Payout transaction block hash is the block hash committed inside the kickoff, like inside the kickoff transactions witness. So this input actually has a witness checksig here. It verifies a block hash's signature. This is the block hash that the operator paid the payout transaction. And we also have latest block hash, which also committed here as the latest block hash TX. So these three things are actually public inputs, and the deposit constant is calculated during the deposit, and then we hard code it to the BitVM. So yeah, this is the bridge circuit part. This is the header chain work only. Bridge circuit host is to generate the inputs of the bridge circuit, basically. And we have a BitVM client here. It's basically so BitVM works in a way that we wrote the gross 16 verifier in Bitcoin script. We made it in a such way that we split it into chunks, and then the operator commits to every intermediate step, and then we have a bunch of disproof scripts where we can disprove any invalid proof. So the BitVM cache is basically generating those disproof scripts once, and then replacing it with the correct internet's public keys, and then using these disproof scripts inside the disproof connector. So the disproof connector is this. So this disproof scripts has hundreds of Bitcoin scripts, hundreds of spanning paths. It can only be executed if the operator's proof is incorrect. And yeah, you've basically put with a dummy Winton's key and then get the places that we need to be replacing in the future. And where is it? So yeah, we have these assertions. We can generate the assert witness data. So the operator has the witness secret key, so it can get the derivation path from here, get assert derivations. These derivations are for kickoff, BitVM assert, and challenge egg hash. So kickoff means the block hash winternets here. BitVM winternets here are these mini asserts, these Z1, Z2, Z100, Z101. These are the BitVM winternets ones. And challenge egg hashes are this challenge egg transaction that it's basically the pre-image that the operator has to reveal when a watchtower sends a challenge. So yeah, this is that. Okay, this is auto-generated. We have the aggregator. Let me scroll down to new deposit. So this is the main function that's being called when a deposit happens on Bitcoin. We create the deposit data, we get the verifiers, and then we first get the nonce streams. These will generate get us public nonces. And after getting the public nonces, we also create a channel for deposit signing. So the idea is the whole process here is doing in parallel. Like whenever we get new public nonces, the aggregator immediately aggregates them and sends the aggregate nonces. While doing so, the operator also immediately aggregates partial signatures and sends the final signatures. Yeah, we create the deposit sign streams here. We basically create all the streams. Oh, we have this create n of n SIGH stream, which is, so we need to pre-sign a lot of transactions. And this is the stream for what needs to be signed. And basically, aggregator is using this stream to aggregate signatures. Verifiers are using this stream to first sign the signatures, partially sign the transactions, and also verify the final signatures as well. So it's going through operators, and then we have some database caches here, but for every operator and every round, and for every kickoff that needs to be signed, we basically sign and then yield all the C caches. So this signing mechanism is using something interesting. Let me show you that one as well. Is it here? Okay, we have transaction type for every transaction, and we have the gRPC proto messages for every of them. These are converter. For example, yeah, create multiple transaction. We have this transaction handler builder, which is used to create a transaction. Most of our transactions are version 3 because we are using Truk sending Truk packages. Basically, we do child pays for parent with an anchor output. And this way, we don't need to calculate any fees in advance. We can just send them at the time of when we're sending it. So yeah, we put the version 3. We put the transaction type here. We don't store this signature because it will be sent immediately. We get the spendable transaction. It doesn't have any sequence numbers, so it has a default sequence. Output is, it has two scripts. One is n of n script, the other one is security council script. And we also add the anchor output. So after doing finalize, it creates the TX handler. And these TX handlers can be signed by actors easily. Where was it? Yeah. For example, this will sign a TX handler. Okay, this sign txends is a function of tx handler. It will get the signer as an input, and it will just sign whichever input it can sign. Okay. So this is, for example, emergence stop tx handler. All these create something, and tx handler functions are matching with the transactions here. They need to match. We have also replacement deposit. This proof taproot output. So we do some kind of caching here. Since all the disproof scripts are kind of constant and these taproots are working in a Merkle tree way, we first calculate the root node, and then we add a hidden node. So if this proof path is hidden node, it's basically the Merkle root of all the disproof scripts. Sometimes when we're sending the disproof transaction, we need them there. So we use this extra script here. And yeah, these are mostly transaction creators. So this builder folder is mostly for creating transactions, signing transactions, and those stuff. Config is, we have two ways to get the config. We get it from environment, we can get it from TOML files. This is the main bridge config, but we also have the protocol param set, which is kind of constant. It has all these time locks, collateral amounts, finality depths, start height, genesis height. And yeah, so this transactions, this kickoff transaction and round transactions are non-standard. The outputs are zero sat. This way we can save up from a lot of fees, a lot of dust value things. So these are non-standard, but we also wrote the code in a way that we can make these standard. So for example, this is also one of the parts of protocol parameters, bridge non-standard. If it's set true, it uses zero sat output for round transactions and kickoffs, except the collateral. Okay, we have the database. So this is the main tables we use. We store the header chain proofs. We store the deposit signatures here. This is I think, the most important table. But yeah, we also store the BitVM setups. We have this Bitcoin sinker that I will get into it in a little bit. We basically index every spent UTXO, like which transactions is spending which transactions, so that we can keep track of everything during withdrawal. Like if a challenge happens, if the operator needs to send the kickoff, if the operator needs to send challenge acknowledge transaction, we do this with this table. And we also have this TX sender. I will get into that as well. But other than that, this database folder is basically pure SQL, saves it to the database, and gets it from there. So RPC includes the proto definitions. All the new deposit flows are living here for the aggregator. Yeah, we have some interceptors for checking the TLS signatures. Some helpful functions here. Okay. Let me see if I forgot anything. Let me talk about this extended Bitcoin RPC a little bit. This is basically, scroll down, our Bitcoin RPC. It can get current chain height. It can check an operator's collateral. Doing these with Bitcoin RPCs, all of these. Yeah, you can get the blockage of the transactions. These are basically wrapper for some RPC commands. For example, this gets the info by height, and it needs to do 2 RPC calls. So yeah, this is that. Okay, TX sender. It has a signer inside it. It needs to sometimes sign extra values. It has obviously Bitcoin RPC. It has its own database. It has a lot of tables to that. But the main idea is sometimes we need to send transactions with some conditions. For example, whenever operator sends a kickoff, operator immediately sends this challenge timeout transaction to the TX sender. But this transaction can only be sent after 1.5 days, meaning that it cannot be sent immediately. But the operator saves it and persists it to the database, and then it will check if it can send it by having the info about the time lock. And yeah, these are for the calculations. This is for getting fee rate. Where is the... So yeah, insert, try to send transactions. So we have this transaction metadata. We have this full transactions. We have fee paying type. Okay, why cannot call this to one? Okay, it can be either child pays for parent or RBF. For example, for Watchtower challenge transaction, it's RBF because Watchtower needs to add additional inputs here to pay the fees. So yeah. So cancel out points, meaning that if that out point is on chain, it will cancel sending these transactions. This is same for cancel TXIDs as well. If that TXID is on chain, it will cancel it. It will just not send it. Activate, meaning that without seeing that TXID on chain, it will not try to send the transaction. And it has some relative block height time locks, meaning that if we set it 5 here and TXID as the TXID of kickoff, it will send the challenge timeout after 5 blocks, seeing the kickoff TXID. So if you want to send the challenge timeout 1.5 days after kickoff, we would set 216 as the relative time lock, and then put the TXID of the kickoff and then send it. Okay. And this is the same for the out point as well. Sometimes we need to make sure. Okay, this is like, this is not after seeing the out point, but this is after that out point is spent. But yeah, it saves to the database. So here's the thing is that, as I said, every operator runs their own verifiers. And this TX sender is only run by the verifier, which means that whenever operator is trying to send a transaction, it saves it to the database, and then the verifier it's running will basically run the transaction, send the transactions whenever it's possible. Yeah, this is the main function that we use mostly. This is checking the transaction types and doing, for example, yeah, this watchtower challenge timeout is only activated when the kickoff's corresponding UTXO. Okay, this is canceled if the watchtower challenge is sent. So what I'm saying is, so that we have this watchtower challenge timeout transactions, and it means that if a watchtower doesn't send a challenge, after 2 weeks, we can send the timeout transaction. But if there is a watchtower challenge timeout, we cannot send these transactions anymore. So we need to cancel it. So we add this kickoff TXID's corresponding UTXO in the cancel out points, and if that out point is spent, which means we have a watchtower challenge, which means we don't need to send the timeout. And yeah, we can do it with child pays per parent. So yeah, transaction sender working is like this. And we have this state manager. State manager it's keeping track of every operator's rounds and every operator's new kickoff. So yeah, operator state machine is keeping track of operator's collateral. Which round is this operator on? And we also have kickoff state machines. It's like whenever an operator sends a kickoff, it can be either a malicious kickoff or an honest kickoff. An honest kickoff, none of the verifiers will try to challenge an honest kickoff. But the operator itself needs to be ready if a kickoff gets challenged. So this state machine is always checking if there's a challenge, if it needs to send the asserts, if it needs to send the proofs. Yeah, stores if the kickoff challenged. And all these state managers are persisted to the database, so that's also really important. Yeah, it has this database. And it also uses PGMQ, which is a PostgreSQL-backed queue mechanism to get the finalized blocks. So another important thing is like this state manager runs on finalized blocks. TX sender works on the latest block, Bitcoin block, because TX sender needs to make sure that the transactions is getting mined. It needs to bump the fees if it's not getting mined. Those stuff. State manager is just coordinating which transactions needs to be sent. Yeah, it can load from the database. It has own round machines and kickoff machines. And this is the saving part. Okay, let's, for example, look at the kickoff. There are several events. It can get challenged. A watchtower challenge can be sent. An operator can send an assert. This is, for example, if another operator sent asserts, we want to make sure we check the proof itself. If the proof is an invalid proof, we want to disprove the operator. So yeah, these are basically the events. And there are some duties. Yeah, handle duty. So operator and verifiers have their duties. Okay, this is under automation, but Yeah, if, for example, send operator asserts duty is called, it will call itself send asserts. And this is basically, as you can see, it's getting the verification key of the proof. It creates all the TX handlers for the current kickoff. And now it's getting all the details that needs to be done for a proof. And it gets the bridge circuit. So we have some also additional testing flags here, which means like we sometimes disrupt some data about, for example, challenge sending watchtowers, just to make sure we also test the case that where operator putting incorrect proofs. Yeah, generate assertions. So first we need to get the gross proof. Okay, so we call the proof bridge circuit. This is coming from the host, bridge circuit host. We get the gross 16 proof. So this gross 16 proof is using our custom RISC-0 gross 16 wrapper. It's out of the scope, but it's the only important thing is like it has a single public input. There's Blake tree hash of bridge constant, bridge circuit constant, and the public input of the circuit. And even after getting the gross 16 proof, we need to generate assertions. So this is about the BitVM. It's basically generating what needs to be signed by the minternids as the asserts, BitVM asserts. And now it's generating the create commitment transactions, assert commitment transactions. And as you can see here, it adds the assert transactions to the TX sender. And the TX sender will send it, and then if the proof is correct, operator won't get disproven, and then the operator will get the reimbursement after some time. We have the music too. We use it from sec p from the latest commit. It's not in a release yet, so we do have these kind of type conversions here. But it's basically aggregating nonces, aggregating partial signatures, creating nonce pairs. This part is important. We want to make sure we don't reuse a nonce, because that would leak the private key immediately. Did I miss anything? Oh yeah, we have some tasks. This is, for example, metric publisher task. This payout checker is a task of operator. So let me describe your handle finalized. Every verifier is handling finalized block of Bitcoins, and then it first gets the Citrea L2 height range. For a Bitcoin block, it gets the Citrea block range, and then it updates the Citrea deposit and withdrawals with that range, meaning that we only care about the finalized Citrea state. We do that with the getting lifetime proofs. And we also, let's go here. So collect deposit move TXIDs, collect withdrawal UTXOs. So we have this withdrawals table. So this move to all TXID is basically the deposit, and withdrawal UTXO it's written in the Citrea state is the UTXO that needs to be spent to finalize this payout. So what we're doing here is like the first deposit goes to the first withdrawal, the second deposit goes to the second withdrawal. And yeah, we save the corresponding deposit, we save the corresponding withdrawal, and also operator's payout checker checks that if it paid the withdrawal, because operator's withdrawal endpoint, operator can also manually pay the payout. So with this payout checker, it just scans the Bitcoin index we have, and then puts the payout transaction, puts its own key here. So we use this info while we're sending the kickoffs. So this is one of the tasks. Yeah, this is the task manager. Forget anything, handled, finalized. Okay, let me lastly talk about the replacement deposit. So replacement deposit is basically, as you can see here, in the normal deposit, it has this address of the user. But replacing is whenever a bug happens, if there's a bug in BitVM, we need to update the system. We replace, using the security console, we replace every multiple transaction. We need to spend this UTXO because this blue arrow is still usable. So we need to change it. So we need to spend it with the new multiple transactions. So we create this replacement deposits where instead of having Citrea address here, it has the old multiple TXID inside it. And with that info, we can update the bridge contract depending on that. So for example, this replace deposit, it updates the corresponding deposit. So yeah, I think that's mostly it. Do you have any questions?
For now, I wrote down a few. 1 second. So what is this like refund transaction that you mentioned regarding the operators?
Reimburse?
Yeah, exactly.
Do you mind if we have like 2-minute break? I will get some water.
Yeah, sure, that works for me.
All right, I'll be back.
I'll also be back for a second.
Okay, I'm back.
Yes, me too. Yeah, so the question was like, what exactly is the reimbursement transaction and what do we need it for?
Okay. So reimbursement is, so operator pays this payout transaction, and operator also can cut some fees, like pay 9.9 instead of paying full 10. And operator needs to get reimbursement. This is using the presigning.
So the operator itself provides the money that gets paid out, and he gets it later from the move to wallet UTXO.
Yeah, yeah.
Okay, makes sense. Yeah.
And the whole process is basically, it sends the kickoff. If it's not getting challenged, it sends the challenge timeout transaction, which spends this kickoff finalizer connector, meaning that this kickoff is now finalized. And then the operator burns every unused kickoff connectors here. So the first 3 here is that the kickoff connectors. It basically burns it. Then it sends the ready to reimburse transactions. If it forgets to burn it, then the operator can get slashed, unspent kickoff connector tags. So yeah, operator burns them, advance the system to the ready to reimburse. So this ready to reimburse transaction is just, if a kickoff is not finalized, then the operator can get slashed. So operator also want to make sure that every kickoff is finalized by either challenge timeout or disprove timeout. So after making sure, if there's no unfinalized kickoff, operator waits 1.5 days and then sends the next round transactions. And then operator can send the reimburse transactions. So we have these round transactions because operator can facilitate multiple withdrawals in parallel with the same stake of 2 Bitcoin here. So this is one of the key improvements of round transactions. So what happens if it gets challenged? If it gets challenged, operator cannot send this challenge timeout transaction. Then we enter this challenge period, because the only way to finalize this kickoff is to send this disprove timeout transaction, but the operator can send it after 5 weeks. So in that 5 weeks, we need to have a resolution on the state of if the operator is malicious or not. So first, we wait for watchtower challenges. Every watchtower sends challenge. Some of them doesn't send. Operator acknowledges all of it. If an operator fails to acknowledge, we slash the operator by challenge not acknowledged transaction. And then after acknowledging all the challenges, operator sends this latest block hash, which needs to have more total work than the maximum of these watchtowers. And it also sends all the asserts. It generates the BitVM proof. It proves that it paid the payout. It proves that the in Citrea state, it paid the correct payout. And this payout transaction was on chain. And then if the proof is incorrect, anybody will be able to send this disprove transactions. Note that this disprove transaction is really large. It's like 4 megabytes. So it's a non-standard full block transaction. Only miners can mine it. So it cannot be propagated through P2P layer, but it's highly profitable because it burns the whole collateral. If it's not getting disproved after 5 weeks, the operator sends this disprove timeout. And this challenge transaction is basically pays the operator. So it's paying 2 things. It's paying the opportunity cost of getting the reimbursement 5 weeks later, and also the money that is needing to send these assert transactions, because these assert transactions are also not that small as well. They are large.
Also, where does this 1 Bitcoin then come from? Who pays for that?
Okay, so this is, anybody can send it. We call it challenger. So this part is kind of out of scope, but the challenger puts the EVM address in the op return of this challenge transaction. And if the challenge was successful, if the challenge resulted in the situation where the operator gets kicked out, then this challenger gets more than 1 BTC. But this is kind of off-chain for now. We can do it in a Citrea smart contract, but this is out of scope for now.
All right. So in general, for the whole design, I suppose the reimbursement function is there so that the operator can do the withdrawal, for example, quickly, and then just get the payout later, right? So that the bridging works faster.
Yeah. The whole this is not why we do reimburse. This is not about the speed, but more about we need to pre-sign this NFN to go somewhere. And this can only be going operators. But we need a way to catch a malicious reimburse, so we need to add some time delay here. And what determines a malicious operator is trying to get a reimbursement before paying. So that's why we have this system.
Okay, yeah, makes sense. Also, one more question for the audit. Should we assume that the automation will be on or off?
We can assume it's on.
Okay, perfect. Yeah, I think question-wise, that's it for now.
All right.
Thank you very much.
Thank you as well.
Thank you guys as well. Have a good day.
Yeah, you too.
Bye.
Thank you, you
Bye.
too. Bye.